In this problem, we're told that the blades of a ceiling fan are turning with an initial angular speed of 30 revolutions per second when they are brought to rest with a constant acceleration. We're told that they turn 60 revolutions before eventually coming to a stop. For part A, we're asked to solve for the angular acceleration of the ceiling fan blades. And then for part B, we're asked to solve for the time that it takes the fan to eventually stop rotating. I'll begin by writing down my given information. I know that my initial angular velocity, omega initial, will be 30 revolutions per second. I know that my final angular velocity will be 0 because I'm looking for the moment when the ceiling fan blades have stopped rotating. And I'm told that the fan blades turn 60 revolutions before stopping. While this may not seem obvious at first, 60 revolutions tells me how many essentially degrees or how much the fan blade rotates through before it stops. So that's my angular displacement, right? In other words, how much rotation does the object do before eventually coming to a stop? Delta theta tells me how the angular position of the fan blades change. And so delta theta is talking about how many rotations or revolutions the wheel is going through. Now, in this problem, because everything is defined in terms of revolutions, right? The initial and final angular velocities are given in revolutions, and the delta theta is also given in revolutions. I can actually leave them as they are, and I don't have to convert to radians. However, it is best practice to convert your values to radians when solving problems, especially if some of your values are defined in terms of radians and some are defined in terms of revolutions. You have to use the same unit or your problem will not work out. So what I'm going to do right now is I'm going to convert each of these values to radians for the sake of example. If I convert the initial velocity into radians per second, that would look like this, right? 30 revolutions in 1 second multiplied by that conversion factor of 2 pi radians in 1 revolution. If I do that, the revolutions will cancel, and I will get 60 pi radians per second. And you can leave the pi in there. That'll help make sure that we're not cluttering up our work with a bunch of decimals. All right, my final velocity is 0, so there's no need to convert that. And then my delta theta can be converted the same way. 60 revolutions multiplied by 1 revolution for each 2 pi radians, and that will give me 120 pi radians. All right, now I have omega initial, omega final, and delta theta. Which kinematic equation would you use to solve for alpha given this information? I would recommend using equation number 2 here because we have information about omega final, omega initial, and and delta theta. Alpha is what we're looking for, and it's the only thing we don't know in that equation. So I'll go ahead and write this equation out. All right, and in this case, because the omega final, or the final angular velocity, is 0, I can go ahead and rearrange this equation for alpha. I'll subtract the omega initial squared from both sides of the equation, and then I will divide by 2 times delta theta to get alpha by itself. That will leave me with negative omega initial squared, right? And the negative is outside that squared term. Divided by 2 times delta theta will be equal to alpha, right? We've just done some algebra there to get alpha by itself. I can go ahead and plug in my values for omega initial and delta theta, and that will give me a value for alpha of, right, that would be literally negative. I'm going to use the values here in radians per second because that's best practice. That's going to be 60 pi radians per second squared divided by 2 times 120 pi radians. Put that into my calculator, and I'll get that alpha is equal to negative 47.1 radians per second squared. And if you used revolutions per second for your angular velocity and for your angular displacement, alpha would be in terms of revolutions per second squared, but we typically want everything in radians. So I want to point out that the acceleration here is negative, right? So just as we saw with linear motion, for an object to be slowing down, the sign of its velocity and acceleration must be opposite. In other words, this wheel, if we consider the ceiling fan to rotate, we didn't really have a direction to begin with. So let's say we assumed it was traveling in the counterclockwise position. I'm going to show that on the diagram here, like that. That would be the positive direction. Right? We've defined that previously. So if the ceiling fan was rotating in the positive direction, in order for it to stop, it must have a negative acceleration. In other words, its velocity is becoming more and more negative every second until it eventually becomes zero. So it's a good thing that my acceleration here is negative. It should be because the fan is beginning to rotate more slowly and eventually it does come to a stop. All right, now for part B, we're asked to solve for the time that it takes the wheel to stop rotating. If I'm looking for time, I can use any of the remaining kinematic equations. However, I'll use the first one because it's the most simplistic. I've gone ahead and rearranged the equation for time by subtracting the initial angular velocity, omega initial, from both sides, and then dividing by alpha to get t by itself. When you plug in the values for angular velocity and acceleration, you'll see that they're both negative, and so you'll get a positive time of exactly 4 seconds. And it's important to note that I stored this value in my calculator and I used the exact value when doing calculations later because we don't want to get rounding error by using rounded intermediate values. So I would recommend you store this in your calculator or you just use the answer tool in your calculator as well for temporary storage. All right. So if my final time is 4 seconds, then that means from the time the ceiling fan was beginning to come to a stop, it took 4 seconds. It turned 60 revolutions in that 4 seconds. It had a constant angular acceleration of negative 47.1 radians per second squared during that time. All right, so this concludes our series of examples for basic rotational kinematics without any kind of rolling motion. Please take a look at the next video for an example of a problem involving an object moving both linearly and rotationally.